Often, we compute the expectation of a random variable conditioned on an event or conditioned on the value of another random variable. The conditional expectation of x conditioned on an event m defined on the same sample space where the random variable x has been defined is computed over the conditional distribution of x conditioned on this event. Let's write this down in this case of a continuous x, where we have a conditional probability density function. In that case, the conditional expectation would be this integral, where essentially we are taking the weighted average of the conditional density. The variance of x conditioned on m is similarly the expected value of the conditional expectation of x given m. So that is x minus expectation of x given m squared times the conditional distribution dx. Right. Now, in the case where we are not conditioning, we are conditioning on an event which is the event that another random variable takes on a particular value y, we have the conditional expectation of x conditioned on the random variable y, and this is x times fx given y, x given y dx. Right. Notice that this, we are conditioning on a particular value script y. Notice that this is a function of the value script y. Okay? When we do not specify the value and leave it as the name of the random variable y, then it would be, the expectation would then be a function of the random variable y. And we will talk more about this case. Let's first do a simple example where we have this distribution, the joint distribution of x and y is a constant when y is less than x and they're both between 0 and 1. So they are jointly distributed in this triangle that lives between 0 and 1. This is y, this is x. And we are asked to compute the expectation of x given y. Right. What do we do in this situation? We are going to apply this expression, but to apply this expression, we need the conditional density function, the conditional density function of x given y. The conditional density function f x given y can be found by taking the joint density and dividing it by fy of y wherever the density of y is non-zero. Well, but what is then the marginal density fy of y? We can easily compute the marginal density for a particular value of y by integrating the joint density over the region of x that is valid for that y. So we would be integrating 2 dx, where x goes in this case from that particular value of y to 1. Right? So x goes from y to 1 to dx, and that simply gives us 2 times 1 minus y. when y is between 0 and 1. So then we find the conditional density as 2 over 2, 1 minus y, which is 1 over 1 minus y when y is between, I'm sorry, when x is between for a given value of particular value of y, let's say y prime, x lives between y prime and 1. So when x is between y and 1, we have this conditional density 1 over 1 minus 1 and 0 otherwise. So that is the conditional density. And now we can apply this conditional density to in this expression and compute the conditional expectation. The conditional expectation of x given y equals script y is nothing but integral of x, let's just write the general version for x times fx given y, x given y, right? And fx given y is given by this, right? So this is equal to x times 1 over 1 minus y when x is between y and 1, right? So the result is equal to, x squared goes from 1 to y, so 1 minus y squared divided by 2 times 1 minus y, which is simply 1 plus y over 2. And this is, of course, valid whenever y is between 0 and 1 and x is between y and 1. Right? So we found that given a value of y between 0 and 1, the conditional expectation of the random variable x is simply y plus 1 over 2, which, makes a lot of sense retrospectively when you look at this. It's between y and 1, and the conditional expectation is y plus 1 over 2. It says basically if we know that x is between these two values, it is uniformly distributed between these values, and the expectation is just the midpoint. Right. Now, in general, if we wanted to compute the expectation of x, we could, in fact, use the conditional expectation by first computing the expectation of x given the random variable y and represent this as a function of y, and then computing the expectation of this function over the distribution of y. This is called iterated expectation. It is a divide and conquer type technique. So let's compute the expectation of x using iterated expectations here. Expectation of x given y, the function g of y in our case is 1 plus y over 2. This is the function. Okay, so all we have to do is now compute the expectation of this thing over the distribution of y. But this is trivial because this is simply a constant plus y over 2. the expectation of the constant 1 over 2 is simply 1 over 2, and the expectation of y over 2 is expectation y over 2. Right. Expectation of y, well, we know it from here. This is the marginal PDF of y, and the expectation of y can be computed by y times twice 1 minus y from 0 to 1. When we integrate this, we get 1/3. So then the expectation of x is 1/2 plus 1/3 over 2, which is 2/3. Okay, so we used iterated expectations to compute the expectation of x by first computing the conditional expectation of x given y. In this example, it may not have seemed that this is a shortcut technique, but in certain problems, in certain cases, this can be very efficient. This can be using iterated expectations can be a very efficient way of computing expectation.